Welcome back to Nick's Algebraics. With me today, I have Random Guy.
Hello, I'm a random guy. He pulled me off the street. He was a random guy. He said, "Do you want to make some math videos?" I said, "Sure." And here I am.
Yeah, that's exactly how I did it. And here we are. So, as usual, the guided notes will be in the description, so make sure to check that out. So, today, I'm going to talk about Gauss-Jordan elimination. But before I get into that, let's talk about what row echelon form and reduced row echelon form are. A matrix is in row echelon form if it satisfies these three conditions. So the first condition is any row consisting entirely of zeros are at the bottom of the matrix. All right, so it has to be the last row. The next condition is the first non-zero number in each row is 1. And this has a special name. It's called the leading one. And let me highlight row echelon form too.
It's very essential that you highlight that. No one would know otherwise what we're talking about.
Yes. Okay, and then the third condition is that the leading one in each row is to the right of the leading one in the row immediately above it. We're going to do some examples and you guys will see what I mean by this. And then lastly, for reduced row echelon form, it's in row echelon form and it has an extra condition that every number above and below each leading one is 0. So I will also highlight this. Okay, so let's do some examples. So determine whether each matrix is in row echelon form, and if it is, determine whether the matrix is also in reduced row echelon form. For part A, is this matrix in row echelon form?
I would say so. There aren't any non-zero rows, so but that's like if there is one, it has to be at the bottom.
That's right.
Yeah. The first non-zero number is always one. You can see that. It's got like that staircase of ones. That's always a good sign. What was the third condition? The leading one. Yep, that looks like it's good to me.
Yeah, the leading one of each row is to the right. You see it's to the right of the leading one in the row immediately above it. So
Mhm.
this is absolutely in row echelon form.
I do not, however, think it is in reduced row echelon form because there are non-zero entries in these columns, the leading ones.
Exactly, yeah. For it to be in reduced row echelon form, you can see this condition here says that every number above and below each leading one is 0. So you can see in the second and third columns, above the leading one, it's not all zeros. So yeah, this is only row echelon form. So I'm going to write REF. Okay, part B. What about this one? Is this row echelon form?
No, I mean look at that row of all zeros. It's in the middle. What treason? What heresy?
Yes, very unfortunate. So I'm gonna box that and make a note. So I'm gonna write this needs to be at the bottom of the matrix. So yeah, the first condition is not satisfied. So this is not row echelon form. And automatically it's not going to be reduced row echelon form. So this is actually neither.
This is what would you call this? A cringe matrix?
Yeah, I would say a cringe matrix. Very cringy.
Yeah, you better believe that's the official mathematical terminology.
Yeah, definitely. And let's see, part C. Is this row echelon form?
Looks to me like it is. No zero rows, so we don't have to worry about the first condition. The leading ones, pretty solid.
Yep.
Yeah, I don't know. Looks pretty REF to me.
Yeah, and the leading ones in the rows
Yeah, yeah, they're all to the right of the one above it. So it's got that. I just look for the staircase.
yeah, that's what the term echelon is referring to. The term echelon refers to the stair step pattern formed by the non-zero entries of the matrix. But yeah, this is definitely row echelon form.
Indubitably.
Yes, indubitably. Now that we know it's row echelon form, is it also reduced row echelon form?
I would say so because all the leading ones are in columns where every other entry is zero.
Exactly, yeah.
Yeah, this is like the textbook RREF.
I wanted to start off with a classic RREF situation. So yeah, this is row echelon form. And because all the leading ones have zeros above and below them, that means it's also reduced row echelon form.
In fact, this is just like an identity matrix.
Yeah, it's an identity matrix.
So would you say that all identity matrices are RREF?
I would. Yeah, that's absolutely right. Okay, now it's going to get slightly tricky. So part D, is this row echelon form?
Okay, so first of all, we have a zero row and it is at the bottom. It is the only zero row, so the first condition is met. Could you scroll up to the second condition? Okay, so the first non-zero number in each row is one. The second row is a little sus.
Yeah, for the second row, the first non-zero number is 2, not 1. So that means the second condition is not satisfied. So this is not row echelon form. And that makes it automatically not reduced row echelon form. So this is neither.
It's a cringe matrix.
Another cringe matrix, yeah. So let me just make a note. This is not a leading one.
Hypothetically, what if that were a one?
I think we're gonna have something similar to that soon. But if that was a one, then it would be row echelon form. And it would also be reduced row echelon form because everything above and below the leading ones are zeros.
Yeah, people would get thrown off by the second column, but do not be led astray by that.
Exactly, because if this was a one, it's still to the right of this one. It's just a little more to the right. It doesn't have to be immediate right. It can be 2 places to the right or 3 places to the right, which we're gonna see right here.
It's almost as if I knew it was coming.
Yeah. Part E, is this row echelon form?
Well, I don't see any zero rows at the bottom or otherwise. But leading ones we do in the first column. Um,
You mean
we
first
do
row?
have, yeah, you know what I mean. Uh, yeah, it looks REF-ish to me.
Yeah. One is the first non-zero entry of each row, and this one is to the right of this one, the one immediately above it. And like I said earlier, it doesn't have to be immediately to the right. It doesn't have to be right here. It can be the one could have been right here, and this could have been a zero, and it still would have been row echelon form. So yeah, this is row echelon form. And is it reduced row echelon form?
Well, you see, the thing there is that you see that one in the middle there in the bottom row. It's got like a negative one above it. That is not a zero. So you have a non-zero entry in the same column as the leading one. So not RREF.
Yeah, so this is just a row echelon form. And what about this one?
Okay, we have the zero row at the bottom. That's good. The leading ones are to the right of the ones above them. That
Mhm.
seems to be satisfied. So I would say that this is REF.
Yeah. And the first non-zero entry of each row is 1, except for this row, of course. This is definitely row echelon form. And now the question is it reduced row echelon form?
I would say so. You see, the five and the three is that's what's going to throw people off because they're like, hey, you have non-zero entries, but there's no one, there's no leading one in that column. So it's like it's not really causing any trouble. The leading ones all have zeros above and below, so we're good.
Exactly. So this is also reduced row echelon form. All right. So I just wanted to dedicate this page to reviewing that because it's going to be important. So indubitably, yes. Let's do example 2, and then I'll get to elementary row operations.
Okay, do you want to do this the old high school way or the matrix way?
We are going to do this the matrix way. So
Who would have guessed?
to solve this system of linear equations, the first thing I'm going to do is I'm going to write this system in matrix form. So I'm going to ignore the variables, I'm going to ignore the x and y's, and I'm just going to write the coefficients and the constants.
So this will be an augmented matrix.
Exactly, that's called an augmented matrix. So let's write this. Okay.
So like the first column is going to be X, the second column is going to be Y, and the third column will be the constants. You don't really write that normally, but like that's just a good way to visualize it. Yeah, the coefficients. of the first equation are 1, 3, and then we have a constant 11. So we can write that in the first row.
Yeah, 1, 3, and 11 here.
And then the second row is going to be for the second equation. And that will be 3, 1, and 9.
Yes.
And since this is an augmented matrix, are you going to write like that line?
I like to put the line. I know that some people don't write it and it's implied, but
Those people are objectively wrong, in my opinion.
yes,
The line is necessary, I think.
yes. So let me just write the vocab board out. So this is called the augmented matrix of the system. The augmented matrix is just a matrix that's derived from the coefficients and constant terms of the system of linear equations. And I like to put a vertical line separating the coefficients of each variable and the constants, but technically you don't have to put it, but I like to put it.
I agree.
So the augmented matrix is a nice compact way to represent and solve a system of linear equations. Now that we have the augmented matrix, to solve this system, let's use elementary row operations to write this matrix as a row equivalent matrix in reduced row echelon form. So let's talk about what the elementary row operations are. So there's three of them. You can interchange two rows. You can swap two rows. That's
It doesn't matter like what order you wrote the equations in, so why should it matter what order you put the rows in, right?
exactly. And you can multiply a row by a non-zero constant.
Yeah, because they're like just equations, right? So if you multiply a number to both sides of an equation, it doesn't fundamentally change anything.
That's right. And lastly, you can add a multiple of a row to another row. And here's another vocab word, row equivalent. I used it earlier. So two matrices are row equivalent if one can be obtained from the other by a finite sequence of elementary row operations. All right. So like I said, to solve this system, we're going to use elementary row operations and we're going to write this matrix as a row equivalent matrix in reduced row echelon form. So I want to end up with something like this. I want 1, 0, 0, 1, and then the solutions like A and B, let's say. So when it's in reduced row echelon form, I can easily see what the solution is. I can see over here, this is 1x, so x equals A, and this right here is y equals B. All right, that's what we want to end up with. Okay, so let's do that. Again, I want this.
You just erased it and you wrote it
Yeah,
again.
yeah, that was kind of unfortunate. So we got the 1 here, so that's good. Now I want this entry right here to be 0. So how am I going to make that 3 a 0?
So first of all, we're going to replace row 2 with
Yes.
row 2 minus 3 row 1.
Yeah, so I can multiply this row by -3. So this will be a -3. And then you add them, and this will become a 0 right here. So I'm going to do -3 times the first row plus the second row, and this will replace the second row. Or you can do it the way random guy said, addition is commutative, so you can write it as row 2 minus 3 row 1. That's also valid, and that will replace the second row. So -3 times 1 is -3, and then add it to the second row. This will become a 0, just like we want. 3 times -3, this will become -9. And then I add 1 to it. That's going to become -8. And 11 times -3 is -33. And then plus 9, that's -24.
There's a lot of arithmetic involved in these questions.
Yes, very easy to mess up on the arithmetic.
I would like to ask a question for the audience. They would like to know probably why would you try to make that 0 there first rather than making the 0 like in the first row, second column? Some people like don't know what order to do the operations in.
That's a very great question. We are going to get the 0 here first instead of here because the way to get a 0 here is I have to do -3 times the second row plus the first row, and that will replace the first row. So if this becomes -3 and then I add it here, this will become 0. But look what's going to happen. Then this will become -9, and then I add it to the 1, this becomes -8. Now you don't have a 1 here, so you did one good thing, but it led to something that you don't want also. So we got 1 here, that was already given to us, and then we have 0 here, so that's great. We're getting closer to reduced row echelon form. Now I want a 1 here. So how am I going to make that -8 a 1?
Let's just divide -8. Like we're multiplying -1/8 to the bottom row.
Exactly, yeah. So we just have to do -1/8 times the second row, and that's going to replace the second row. So that's one of the elementary row operations, is multiply a row by a non-zero constant. We're allowed to do that. So when you do that, -8 times -1/8 is 1. That's what we wanted. And then -24 divided by -8 right there. Dividing by -8 is the same thing as multiplying by -1/8, and you'll get 3. Okay?
Now this looks like REF, but it doesn't look like RREF. Not yet.
That's right. So lastly, I want this to be a 0.
Now I'm seeing why it was important that we made the 0 in the first column, because now we can like deal with the second column without worrying about like messing up the leading one in the first column.
Exactly, yeah.
You can add or subtract a multiple of 0, it's not going to mess up that first thing. So let us replace row 1
Mhm.
by row 1 minus 3 row 2.
That's right. I'm going to do it the other way around. I'm going to say -3 row 2 plus row 1, and that's going to replace row 1. -3 times 1 is -3, and then add it to 3, that becomes 0. By the way, right here, if I do 0 times -3, that's 0, and if I add it, that 1 stays there, which is what we want, which is why I'm doing it in this specific order. That's what random guy said. And then for the last column, -3 times 3 is -9, and then plus this 11 here is going to be 2.
It was already 2, just in Roman numerals.
Yeah. We wrote this augmented matrix as a row equivalent matrix in reduced row echelon form. It's row equivalent because this can be obtained from this by doing a finite sequence, just a couple of elementary row operations. Okay, so now that it's in reduced row echelon form, we can easily figure out what the solutions are by converting it back to, a system of linear equations. Remember, this is the column for x, this is the column for y, and this is the column for the constants. So right here we have 1x plus 0y equals 2, which is just x equals 2. And over here we have 0x plus 1y equals 3. So that's just saying that y equals 3. And that's our solution. I can write it as an ordered pair, so I can write this as 2 comma 3.
There you have it.
Yeah,
Where the two graphs cross, the two equations would cross if you graphed it out.
that's right. One thing I wanted to mention is no matter which elementary row operations you use, the reduced row echelon form of a matrix is the same. So every matrix has a unique reduced row echelon form. So no matter how I did this, I would end up with this.
The same is not true of REF. That could have multiple forms.
That's right. Yeah, row echelon forms are not unique. So different sequences of elementary row operations can result in different row echelon forms. All right. So what we did right here is something called Gauss-Jordan elimination. This is a great way to solve a system of linear equations. So the first step is to write the augmented matrix for the system. That's what we did right here. And the next step is to use elementary row operations to rewrite the matrix to a row equivalent matrix in reduced row echelon form. Again, to get reduced row echelon form, you need to get a 1 in the upper left-hand corner of the matrix. And then you use that 1 in the first column to get zeros below it. Like what we did right here to get a 0 below that 1 right there. We did -3 times the first row, and we added it to the second row, and we got a 0 there. And then once the first column's done, then you move on to the second column, second row, second column, and you get a 1 here. And you use that one in the second column to get zeros above and below it right here. And once you're done with the second column, then you're going to move on to the third row, third column, and get a 1 there. And then you use that 1 in the third column to get zeros above it. And then you continue this procedure as far as possible.
Yeah, a lot of people, I think this is the really hard part for a lot of people, knowing which order to do the operations, because everything else is pretty simple. Like you need to do the right strategy so that you don't mess up the entries you already fixed.
Exactly, yeah. We're doing it in this specific order so you don't mess up like a leading one you had at the start or something like that.
Yeah, although some matrices aren't going to be like in this 3 by 4 or 3 by 3 or whatever. Sometimes they'll be a little bit uglier, like a 2 by 4 or something, which is why it's important that we do the first section so at least you recognize what row echelon form, I mean, sorry, reduced row echelon form looks like. Because they're not always going to have this nice staircase. You might have those columns with no leading ones in the middle, and you might get tripped up by that.
Yeah, you can have some really cringy matrices out there that
No, cringe. We use it to mean something else. That means it's neither REF or RREF. Remember, this is formal terminology. You better believe it.
yes.
Don't fact check that. Just trust me.
Yeah. Source, trust me, bro. And once you do that, then you use the reduced row echelon form of the matrix in step 2 to write the system's solution set. So like I said, once you're in reduced row echelon form, then you can pretty quickly see what the solution is going to be.
Yeah, you just look at it.
Yeah, just look at it. Okay. So that's Gauss-Jordan elimination. That's what we're going to use to solve the systems in the rest of this video. And that's what we've been using, for example, 2. All right. So let's do example 3 now. Now we have a more bulky system of equations. So
You can see why this would really suck to do it the normal way in high school of like substitution and elimination. With 3 by 3, it gets messy, and if it's like a 4 by 4 or higher, then oof.
yeah, then you're really going to want to use matrices.
That's why you need linear algebra.
That's right.
So we should start by writing I guess we'll do three first. The augmented matrix, just the coefficients on the left, then we have a bar, and then we have the constants.
Yeah.
And you're using x1, x2, x3. Sometimes you see x, y, z, but I like this more. It's more general. Because what if you have like x4, x5, f6? You'd run out of letters eventually.
Yeah, and I don't like W and like, all those other variables.
Yeah, this is better.
Yeah.
So
So,
we'll have 3, 1, -2, and then 5.
yep.
So that's the first equation. And you can write these in any order, but we'll just do the one they're giving us, or that Nick gave us.
Yeah.
So we have 1, and then you got to be careful because there's no x2 term. So it's really 0 times x2.
Yep.
And then -3, -2. And then we'll have 2, 2, 1, 4.
Beautiful. Let me
I know. Thank you.
just
I know I am.
All right. So back to this table here. The first thing is we want to get a 1 in the upper left-hand corner. So how am I going to make this a 1?
So one thing you could do that I wouldn't do, but that you could, is just divide by 3. So multiply 1/3 to the first row, but then you're going to get some weird fractions, and that's going to be annoying. So why don't we instead replace row 1 by row 1 minus row 3?
Well, I have something even better. I'm going to just swap the first row and the second row.
You could do that as well.
Yeah, I highly don't recommend multiplying this row by 1/3 because, like Random Guy said, you're going to get fractions, and we're trying to avoid that all. So the easiest thing you can do is just swap the first and the second row. So if you swap the first and the second row, you're going to get this matrix. And you can see now we got a 1 in the upper left-hand corner. So that's all you got to do.
We even got a 0.
Yeah, there's even a nice 0 there, so that's great. And we even have diagonal ones already, but it's gonna get ruined a little bit, but it's okay.
It will be. It will be. So what is the second step? That would be probably to get a 0 right below it in all those entries.
Yeah, we want zeros below this leading one right here.
Let
So,
us examine how we might accomplish such a feat.
yes, to get a zero here, I need to multiply the first row by -3 and add it to the second row, and this will become 0. And it's the same idea for making this 0. I just need to multiply the first row by -2, and then I add it to the third row, and this will become a 0. All right, so -3 times row 1 plus row 2, and that's going to replace row 2. And then -2 times row 1 plus row 3, and that's going to replace row 3.
I usually like to write the row and the arrow like before the operation, but that's just the way I learned it.
Oh, so you wrote like,
Like, all right, row 3 goes to -2r1 plus r3. That, yeah, I like that.
oh,
I guess there's no wrong answer, much to my chagrin.
okay. I guess that works too. I haven't really seen it that way, but that's it.
That's the way my professor did it.
Okay. Well, I don't like your professor. So,
That's every time you criticize my professors, I'm gonna let them know that you said these things.
yeah.
You said the same thing about my Calc 3 professor.
Yeah, with the gradient, putting an arrow on top of the nabla symbol, that was,
I noticed that arrows are the problem in every one of these criticisms.
yeah, it's always an arrow.
If you insist, we'll do it your way, just for consistency's sake.
Of course.
Actually, I shouldn't use the word consistency. That has different meanings in linear algebra.
Yeah.
Anyway, let's get back on track.
Yes. So let's see. Let's do the arithmetic. So -3 times the first row, this will become -3. This stays 0. This becomes 9. This becomes 6. And then I'm going to add it to the second row. So -3 plus this 3 right here, that's 0. 0 plus 1 is 1. 9 plus -2 is 7. And this will become an 11 because we have 6 plus 5. So we got 0, 1, 7, 11 in the second row. All right. And for the third row, so we're going to multiply the first row by -2. So this is -2, 0, 6, 4. And when you add that to the third row, the -2 and the 2 will cancel and you get 0 here, just like we want. 0 plus 2 is 2. 6 plus 1 is 7. And 4 plus 4 is 8. So you have 0, 2, 7, 8.
We're getting somewhere.
Yes. So now the next thing is once we got these zeros here below the leading one in the first column, now we want to get a 1 in the second row, second column. And luckily, we already have that. So,
Yay.
yeah, so we can
I'm
just,
so happy.
I know it's beautiful. And then we can just move on to this. So, we're going to use this one in the second column to get zeros above and below it right here. And luckily, we already have a 0 above it, so we just need a 0 below it now.
Let us replace row 3 with row 3 minus 2 row 2.
Yeah, so I'm going to multiply this row by -2, so -2 row 2, and add it to this third row, and that will replace the third row. Okay, so this becomes -2. We add it here, it becomes 0. This becomes -14. Add it to 7, you get -7. This 11, when you multiply it by -2, becomes -22. And plus 8, that's -14. All right. And then the next step is now that we got zeros above and below this leading one in the second column, now I want to get a 1 in the third row, third column. So right
Well,
here,
that's a simple matter. Just divide, or sorry, let's multiply by -1/7.
yes, -1/7 times the third row. -1/7 times -7, that's 1, just like we wanted. And -1/7 times -14 is just 2.
This is gorgeous. And this is an REF now, right?
That's right. This is row echelon form.
If you were so inclined, you could already see that x3 or z, if you want to call it that, whatever, x3 is equal to 2. And then you could sub that into the second equation, and you could solve for x2 and then into the first equation, and you could already solve it this way. That's called back substitution. But we're doing Gauss-Jordan elimination. So we're going to do RREF. So we can not even have to go back to the original equations. We can just do it all in matrix form.
Yes.
Let's get those zeros in the third column.
Yeah, now that we have a 1 right here, I want zeros above it. So just like last time, I'm gonna multiply this row by -7 and add it to the second row. And then I'm gonna multiply this row by 3 and add it to the first row. So
I guess we could have done this step before we did the last one in a sense, because we already would have canceled the 7 and the -7. Now we're multiplying 7 again.
yeah, that's true. There's a couple different ways to do that. Okay, so let's do -7 times the third row plus the second row, and that's going to replace the second row. And then we're going to do 3 times the third row and add it to the first row, and that's going to replace the first row. All right. 1 times -7 is -7, and -7 plus this 7 right here, that's 0, just like we wanted. 2 times -7 is -14, and then plus this 11, that's -3. And now for this, we're going to do 3 times the 1 is 3, add it to the first row, that's going to become 0. And 3 times this 2 is 6, add it to the first row, that's going to become 4.
Would you look at that? We have our solution.
We have
Now you
written,
look at it. This is the hardest part.
yeah, now if you just look at it, you'll see that this first row is telling you that x1 is 4, x2 right here is -3, and x3 is 2. So x1 is 4, x2 is -3, and x3 is 2. And you can write this as an ordered triple. You can say 4, comma, -3, comma, 2.
Interesting.
Yes, very interesting.
Of course, you could have gotten this answer very easily in a couple of seconds using MATLAB, but you can't always do that on an exam.
That's true. Yeah. That's our solution. Again, this is called Gauss-Jordan elimination, what we just did. So now let's do example 4. Again, we're trying to solve this system right here.
Now
So
we're using X, Y, and Z instead of the subscripts for X.
yeah,
You will see it that way, so it's important to know what it looks like.
yeah. So what is the first step?
Be right to the augmented matrix using the coefficients and the constant column.
Yes. What are the entries for the first row?
-3, -5, 36, and 10.
Yes.
Yeah, this step and looking at it at the end are the hardest parts.
Yeah. And what are the entries for the second row?
-1, and we have a 0y that's kind of hidden there, so don't forget that's a 0, and then 7, and then 5.
Yep. And then for the last row?
1, 1, -10, -4.
Yes. Okay, fantastic.
We
So
have a 0 in the middle. That's probably going to get messed up, but it's nice to see, nevertheless.
yeah. So we got the augmented matrix. That's the first step. So now we want a 1 in the upper left-hand corner. So what's the easiest way we can do that?
Multiply by -1/3 is going to give us equal fractions. Not a huge fan of that. So we could add one of the other two rows.
We could.
I know what you're going to say. I know what you're going to say because we did it in the last problem. You're going to swap the rows. So how about 1 and 3?
Yes, the easiest way to get a 1 right here is to just swap the first row and the third row.
Swapping is the elementary row operation that's easiest to forget, I think.
Yes, that's true.
It's arbitrary what order you write these equations in, so why not swap the rows?
That's right.
This is so
Yes,
magical. This is technology at its finest.
yes. Because I'm not writing those numbers again.
Yeah, unfortunately, you have to do that on paper exams.
Oh my God. Every time I take an exam, I'm just like,
You can't use notability.
all my perfect lines are gone and it looks like trash. It's not in
Actually,
blue, it's all in like a gray pencil color.
it's unfortunate, but I'm not doing another free notability sponsorship.
Yeah.
They don't pay us, at least not yet.
Yes, not yet. Okay. So we got a 1 in the upper left-hand corner. So the next thing is use that 1 in the first column to get zeros below it. All right, so just like we saw last time. So I'm going to get the first row and add it to the second row because this 1 and this -1 right here will cancel out and you'll get 0. So row 1 plus row 2, replace row 2. And over here, I can triple the first row and add it to the third row, and I'll get a 0 here. So 3 times row 1 plus row 3, replace row 3.
Oh, we're doing 2 for 1.
Yes.
Yeah, we're gonna lose at 0 in the middle, but we wanted a 1 there anyway.
Yeah. We are adding the first row to the second row. So 1 plus -1, that becomes 0 here. 1 plus 0 becomes a 1. -10 plus 7, that becomes -3. And -4 plus 5, that's just 1. And now I'm going to do this operation here. So 3 times row 1, so 3 here. And then plus that -3, that's 0, just like we wanted. And this becomes a 3, plus the -5, that's -2. And then 3 times -10, that's -30. And then plus the 36, that's just 6. And 3 times -4 is -12. And then plus the 10, that's -2. All right. So we got these zeros below that leading 1.
We have the next one that we want already.
Yeah, good. We have this one right here in
Now
this.
we just gotta get those zeros.
Yeah, now we just got to get these zeros above and below that 1 in the second column. So I'm going to do -1 times the second row and add it to the first row. And that's going to replace the first row. And to get a 0 here, I'm going to double the second row and add it to the third row. And that's going to replace the third row. All right, because if I double this and add it here, this is going to become 0. All right, so let me just go through the arithmetic quickly. This is negative, and I'm going to add that to that 1 there. So that becomes 0. The negative of -3, that's +3. And then plus -10, that's -7. And -1 plus the -4, that's -5. And then if I do 2 times this 1 and then add it to that -2, that's 0. This is 2 times the -3, so that's -6 plus the 6, that's 0. 2 times this 1, that's 2. Add it to that -2, and that's 0.
It's good that we got 0 for that entry. Otherwise, you would have had all zeros on the left equal to some other number, and that would have been inconsistent.
Yes, that would be very unfortunate.
Actually, no, it would be very fortunate because you could just say no solution, and then you're done.
Actually, you're right. I do love it when that happens. I love writing no solution and just ending the problem.
Yeah, unfortunately, we did get a 0 row at the bottom, so
Yes. So this matrix is now in reduced row echelon form. So I'm not going to do anything further now. Let's just interpret what this matrix represents and figure out what we got to do. You know what? Let's write the system of linear equations corresponding to this matrix. So
okay. We're gonna do the opposite of what we did when we wrote the augmented matrix.
yes, so the first row corresponds to what equation?
X minus 7z equals -5.
Yeah. So we have x minus 7z equals -5.
I like to write bars through my z's just to make sure they're not confused for twos. But everybody's got their own style, I guess.
Yeah, I just write my z's, yeah, as normal. And then what about the second row? What is that as an equation?
That would simply be y minus 3z equals 1.
Yes, y minus 3z equals 1. And then what's this?
That would be 0 equals 0, which means nothing. That's not useful information.
Yes. So this is just telling us that 0 equals 0. And it's always true no matter what values are used for x, y, and z. So this,
I'm glad we were able to do this convoluted proof for 0 equaling 0.
yeah, so this equation doesn't give us any information about the variables. But what this equation does tell us is that we have one fewer equation than the number of variables. Because right now we have three variables and only two important equations. So what does this suggest about the number of solutions?
Perhaps there are infinitely many solutions that would work for this.
That's right. So
Because there's like no restrictions on one of the variables.
that's right. One of the variables can be whatever. So to represent the infinitely many solutions of this system, it's convenient to introduce a third variable, t, called a
Oh,
parameter.
doing the parameterization. Oh, I didn't even know you were going to go that far.
Yes. So that's what I'm going to do. I'm going to introduce a third variable, t, and that's called a parameter. And the thing is, which variable is going to be the parameter? Is it going to be x, y, or z? To figure that out, let's look back at this matrix here. Notice how the columns for x and y have a leading one, right?
I
And
didn't notice that. Yeah.
yeah, and the column for z does not have a leading one right here. That means I'm going to make z the parameter. The variable that does not have the leading one, I'm going to make that the parameter. So z can be any real number t. So let me write that right here. So z equals t. So I'm going to replace all these z's right here with t's. So that means z can take any value, and we will express x and y in terms of z now, or I guess in terms of t. Same thing. So I'm going to solve for x here, and I'm going to solve for y here. And again, it's going to be in terms of t. So to solve for x, I just need to add 7t to both sides. So this is going to become 7t minus 5. And to solve for y, I just need to add 3t. So y equals 3t plus 1. All right. So this is the general solution to the system. We have z equals t, we have x equals 7t minus 5, and we have y equals 3t plus 1. And I'm going to write the solution as an ordered triple.
We're not getting it as a matrix.
No, and we're going to have
Okay, you've gone against my professor now.
so we're going to have 7t minus 5, comma 3t plus 1, comma t. This is our solution as an ordered triple. And then t can be any real number.
Depending on some of your classes, maybe some will be satisfied with infinitely many solutions, but this is a bit more specific.
Yeah, it depends on the class you're in. Some classes might just stop right here and say infinitely many solutions and just that's it. But
Probably enough for high school, but in linear algebra, this is better.
yeah. So this is a parametric representation of the system's solution set. So like I said, Z does not have a leading one, so it's going to be the parameter. And X and Y's have leading ones, so I'm going to express X and Y in terms of the parameter T. X and Y are the dependent variables. They depend on the parameter T. So one other thing, this is the general solution, but if you want to get particular solutions, you just need to give a specific value to t. So for example, if t equals 0, this is gone, this is gone.
-5, 1, 0.
Yeah,
That's one possible solution.
that's a particular solution. And if t equals 1, you have 7 minus 5, so 2, and then this is 3 plus 1, that's 4. So 2 comma 4 comma 1. That's another solution when t equals 1.
How about them apples?
Yep. Okay, so now let's do the last example for today. So what's the first step?
Writing the augmented matrix.
Yes,
Good place to start. I'm
absolutely.
already seeing a 2 is going to cancel from everywhere in the first equation. Do you want to bother writing that out and then like doing the 1/2 R1, or do you just want to cancel it out now?
No, it's okay. I'll show the whole thing. So
Okay, of course. I forgot this is your channel. This is Nick's Algebraics.
yes,
Way too many steps.
I try. So the first row is gonna be what? In the
2, 2, 2, 2.
yes. Two, two.
Really 1, 1, 1, 1, but I guess we're gonna do all the steps.
Yeah. And then what about the second row? Second
One,
equation?
one, one, one.
Yeah. I purposely did it like this. So,
I can see that. I can see that. You always have a purpose for what you do.
yes. And then for the third equation,
4, -3, 9, -7.
yeah, 4, -3, 9, -7. And the last equation,
6, -8, 16, 9.
yes, 6, -8, 16, 9. I can't make a bracket normal.
I don't think anyone's gonna click off the video just because of that. I hope.
I hope not.
Someone's gonna do that now just to spite you.
Yeah,
That's my bad. I shouldn't have said that. Please stay.
please, we need the views. So again, I want a 1 in the upper left-hand corner of this matrix. So there's two ways of doing this. I can,
Swap or divide 2.
yeah, I can swap row 1 and row 2, or I can just do 1/2 times the first row. So both of them are equally easy. So I'm just going to stick with 1/2 row 1 replace row 1. Doesn't really matter. Okay. So this becomes ones. So now back to my table here. I'm going to use the 1 in the first column to get zeros below it. All right. So let's use this 1 right here and get a bunch of zeros here. So it's just like the last couple problems. So I'm going to do -1 times the first row, add that to the second row, and that's going to replace the second row. You can see that'll get me a 0 there. And then I'm going to do -4 times the first row and add it to the third row. And then I'm going to do -6 times the first row and add it to the fourth row.
This is a sound strategy.
Yes.
Getting ambitious for doing 3 at once.
Yeah. Now I just have to do a bunch of arithmetic.
It is Nick's Algebraics after all.
It is. So these will all become -1s because we're doing -1 times the first row, and then we add it to the second row. So all these ones right here, when you add them to -1, will all become zeros.
Weren't you gonna name the channel like Nick's Arithmetics or something at one point?
Yeah, Nick's arithmetics. I decided algebraics. I knew back then, like, I don't think I'm gonna keep making arithmetic videos. So
Yeah, but that has changed today.
yeah, yeah, now I'm back to arithmetic.
But it's linear algebraics, so it's still algebraics.
Yeah, there you go. All right, so that's the first elementary row operation. And now I'm going to do -4 times the first row. So this will all become -4s. And I'm going to add that all to the third row. So -4 plus 4, this will become 0. -4 plus -3, that'll be -7. -4 plus 9, that's 5. -4 plus -7, that's -11. So we have 0, -7, 5, -11 for the third row. And then lastly, I'm going to do -6 times the first row plus the fourth row, and that's going to replace the fourth row. So this all becomes -6, and I'm going to add it here. So -6 plus 6 is 0. -6 plus -8 is -14. -6 plus 16 is just 10. -6 plus 9 is 3. So we got, for the fourth row, 0, -14, 10, 3. Okay, so what do you notice now is happening in this matrix?
We have a whole 0 row again.
Yes, and what should we do with a row of all zeros if we want this to be in reduced row echelon?
That sucker at the bottom. You gotta swap it out.
Yeah, remember that's one of the conditions that we started off with today, that any row consisting entirely of zeros are at the bottom of the matrix. So let's do that. Let's just swap the second row and the fourth row. So R2, and we're gonna swap that with R4. Okay. So we got a 1 in the upper left-hand corner. We got zeros below it. So the next step is going to be to get a 1 in the second row, second column. That's the normal Gauss-Jordan elimination way of doing it. But I'm going to do something a little different because getting a 1 there is going to be, you're going to,
Irritate.
yeah, it's going to get kind of annoying. And you're going to want to get a 0 here and a 0 here. Like there's going to be some fractions getting created.
We hate fractions.
Yeah, so I'm gonna go against the Gauss-Jordan elimination process for this next step now. I see a -7 and a 5 here, and I see double that in the row above it, -14 and 10. So instead of getting a 1 here and a 0 here and all that stuff, I'm going to just multiply the third row by -2 and add it to the second row. And by the way, what does this row of zeros, does that mean that we're going to have infinitely many solutions here?
That is the question.
We'll see in the next step, and it'll be really clear what the number of solutions we're going to have is. So -2 times the third row, so this becomes 14, -10, and this becomes -22, and we're adding it to the second row. So -14 plus 14, that's 0. 10 plus -10, that's 0. And 3 plus -22, that's -19. So this becomes 0, this becomes 0, and this becomes -19.
I see what the problem is.
What is the problem?
Adding 0 plus 0 plus 0 cannot equal -19. This is a no solution type of situation. This is an inconsistent system.
That's right.
We saved ourselves a bunch of work.
Yes. I think I messed up on a step. I messed up right here. So -4 times the first row, that's -4 here. And then plus the -7, that's -11. So sorry, this should be -11.
I think I might have noticed that when you were speaking, but I don't know. I guess I didn't mention it for some reason.
Yeah, and then this -2 times -11 is 22, and then plus the 3, that's 25. So this should be 25.
It won't change the answer. Still no solution.
Yeah, we have 0 equals 25 in the second row, which is false. So what
This
does
is
that
fake
mean?
news.
Yes, it's fake news. So what does that mean the solution to this system is?
Perhaps no solution exists.
Yes, that means there is no solution.
Solution, solution. Wherefore art thou solution?
Yeah,
There is no solution.
which is great, which means I don't have to do any more arithmetic. But the reason why I made this specific example is because if you have something like 0 equals 25, then that will always yield no solution. But if you have 0 equals 0, that doesn't always mean you're going to have an infinite number of solutions. So
You got to keep going to check.
yeah, you got to take every row into account.
Okay, don't call it quits just by saying that, and then it
Ex
would be awkward.
Exactly. Yeah. And I even made that clear in one of my videos in the past for solving a three variable system. I did an example similar to this just to make the point clear. So actually take a look at that video because I go deeper into the geometry and like the graphs of each of these equations. But that is it for today. Make sure to subscribe, like the video, leave a comment on what you think, and I will see you guys next time.
Yeah, and comment what you want us to do next.
Yeah.
All right, bye.
Bye, guys.